Hi, my name is Schuyler. I do a lot of Chisel and FIRRTL development, and I'll be trying to provide an overview of what a library is in the Chisel3 Hardware Compiler Framework, which unfortunately is more difficult to classify than you would expect. And then an overview of what some of the different libraries which do exist within this ecosystem, to sort of follow on from the earlier discussions today about Chisel and FIRRTL and how you can make a library for any of these things, as well as how you make a library which cuts across some of the layers in the compiler stack. So the only thing with this is I need to kind of give my overall overview of what a compiler is from the perspective of software, and then translate that into what it means in hardware, because that's sort of critical if you're trying to think about a library that's going to live somewhere in this ecosystem, right? So this is just showing the standard canonical three-stage compiler using sort of my own coloring or whatever. If you go and look up a compiler on the internet, this is what Wikipedia is going to tell you. There's three stages. There's a front end, which is doing some kind of source code intermediate representation transformation. I'll get into some context of what this is later. That then goes to a middle end. The middle end is an optimizing compiler. It reads IR as input and outputs IR on the other end. And then finally, you have some back end, which is reading IR and doing code generation. Okay, so I'm sure you all are able to fill in the blanks based on where Chisel is a front end, FIRRTL is a mid end, and the FIRRTL Verilog emitter is a back end. But the thing is, Chisel and FIRRTL. All right. Okay, I'll just try and talk loud. If you can't hear me, just tell me. So the key thing with this is that just in code, because sometimes I like to actually think about it this way: a front end string to IR, middle end is IR to IR, where there's some number of transforms that you're applying. There's a sequence of transforms, you repeatedly apply them. Adam mentioned something about fold left. This is what that is. And then finally, you have the back end, which is an IR to something. Okay, in this case, some type parameter. So the thing is, while it's like super intuitive that this whole notion of a three-stage compiler makes a lot of sense, not all compilers are built that way or exposed that way nicely to the user, right? So GCC is fantastic, mostly because it compiles Linux. Outside of that, it's a pain. And specifically, this kind of comes down to is like GCC is great if you want to compile C, and you want to compile it for your host machine, okay? You just type GCC. As long as you're not on a Mac, it's actually doing GCC. And then you're going to go from C. Magical things happen, and then you get a binary on the other end you can run on your host machine, okay? If you then want to go and then say, oh, well, I really want to go and build a binary that's going to run on Rocketship, well, then I need a cross-compiler. So I need something which is able to go from C all the way to a RISC-V binary. Okay, so then you wind up with the RISC-V 64 targeting the new lib library that's GCC. Okay. And then the other problem is then what happens if you come along and you have some magical new language which you like or you built or you're a hobbyist, and then if you want to then go and build a compiler for that, well, you're probably going to be re-implementing all the stuff that GCC is already doing. There's a lot of shared optimizations. Things like even what Adam was mentioning, dead code elimination, constant propagation. You wind up just re-implementing all of the algorithms that everybody else already did. So the thing is, where things changed is then you have LLVM, which was a UIUC project done by Chris Latner, which basically said we're actually going to build a three-stage compiler framework. Okay, so LLVM, generally referred to as the LLVM Compiler Infrastructure Project. And it's really not so much about a compiler specifically, but it's about building and optimizing compiler and then building all of the infrastructure around it, which is then enabling you to target arbitrary backends, build new front ends for whatever language you might happen to have. Okay, so this is really when everybody keeps talking about like Chisel and FIRRTL are LLVM for hardware. That's what this is. Okay, so just to reiterate, so before where if we wanted to target RISC-V, we would have to go and then build a cross-compiler. For LLVM, that's just a different backend. And in that sense, then, the LLVM optimizing compiler in the middle is just doing all of the same optimizations on your code, or may add new optimizations. So the cool thing with LLVM is that if you want to go and add a new optimization, all that you have to do is effectively just go and link a new shared library into LLVM, and you can then go and run that, right? And then for whatever front end you have, there's Clang, which is a C or C++ front end, Flang, which is a Fortran front end. There's a Rust front end, there's a Swift front end. If you want to go and build a new language for, say, describing machine learning concepts or state machines or, I don't know, doing web design, whatever, like whatever language makes sense for you, you just have to then go and build a front end which is able to take your language and convert it to an IR, okay? So really, in this sense, this is sort of the overarching motivation of what I've been calling, and I guess Adam originally used this term of a hardware compiler framework. So he uses in this, he had an ICCAD paper 2017 called Reusability is Fertile Ground. So good on the puns, and if you haven't seen the new FIRRTL logo, it uses a nice tree, so we're overloaded, so to speak. But the thing here is that, and this is sort of then how I like to show it, and I guess you saw this earlier in my talk yesterday, but Chisel and FIRRTL are really a hardware compiler framework project, all right? So while on the one hand, I don't want to de-emphasize Chisel so much, but at the same time, like, if you really want to build a new front end that is able to target FIRRTL, you can totally do that. If you want to go and build a new back end which is not emitting to Verilog, but wants to go and emit to VHDL, like would potentially be of a lot of use to IBM because IBM is a VHDL shop, that's something which would be highly beneficial. So the thing is here is just to be completely concrete about this, the front end is Chisel or something else. However, there may be other front ends on top of that, and I'll try and quantify what that is when I start talking about specific libraries. The middle end is the FIRRTL compiler, and the back end is the Verilog emitter. So the thing here, though, is that in addition to the circuit, which is then being passed from the front end to the mid end to the back end, you also have this annotation path, right? Which is the stuff that Adam talked about a lot and provided some examples of, and I'll provide some more examples of in the context of building libraries. But the key thing here is that with the circuit, you want to attach metadata to specific things. So in this case, it's like I would want to inline something in my circuit. But it goes beyond that in an ongoing refactor that we're working on, which is basically allowing you to control the tools using the annotations. So the thing is here, at the Chisel level, or so most of you have probably interacted with the Chisel3 driver, which Jack talked about earlier. You pass a bunch of command line options kind of to that, and one of those options is like -- compiler Verilog, or -- compiler low, which is going to run the low FIRRTL compiler. So the thing is, though, once you have that information, once you then give that to FIRRTL, it's natural to think of what I want to do with my circuit is encoded in an annotation. So this introduces this, actually I'm getting a little bit ahead of myself. But basically what I'm getting at with this is that this notion of annotations allows you to build this hardware compiler framework, because you have a defined interface on what every stage in the hardware compiler framework is supposed to speak. And then if you want to then go and implement something new, all you have to do is align with that API. So it's a little bit of a subtle concept, but it's something which is then trying to then build this out from saying that it's just Chisel, but it's this compiler framework. So actually, let me jump around just a little bit. Actually, oh boy, sorry. So there'll be slides on this later, but generally what this idea of that is you have this communication substrate, and this communication substrate are annotations. Annotations are metadata about 0 or more specific things in your circuit. The notion of being attached to 0 things is something where then you're saying that is something which I am then able to use to then control what the hardware compiler framework process is. A target is something in a circuit, which Adam went into in a fair amount of detail. And then obviously then you sort of have this difficulty of then how you define something. So I just have 2 slides which kind of help me think about this, because when you start writing transforms for FIRRTL or libraries, this comes up a lot. So the thing is, just if you consider this circuit here, you have top instantiates A1 and A2, or top instantiates A twice, top also instantiates C, A instantiates B, and C instantiates B, right? You wind up with this FIRRTL that's then shown here on the right. And the thing is, though, there's sort of 2 main views of how you look at that circuit, right? The one hand is a strict module level view or local view, which is where top is then in the sense of an edge labeled graph, where edges are instance names and vertices are modules. What that is then saying is that this is sort of my view. So the thing is here, then there's some notion of referring to what is A, but then once you unroll that and actually flatten that out, and say you're going and actually then building a circuit, like an actual chip, this whole thing is flattened and you're looking at this complete view or this circuit view on the right. So the thing with this is that you need some capability of referring to every possible permutation of top.a1.b2 versus top but fundamentally what it is that there's a problem when you're trying to then refer to specific things in the circuit. The good news is that Adam was able to figure that all out as he went into significant detail on. But at the current time, at the chisel level, you're sort of left to refer to things at this local view notion. And Adam, Jack, and some of the other FIRRTL developers are working on a good way of exposing the instance annotations at the chisel level. All right. So the question then comes up, what can annotations store? So fundamentally, annotations are something which extend product. So product in the Scala sense is a Cartesian product, which basically means that it's a cross product of all the possible things which could fit in for some parameter. All right. So in the case of tuples are extend products. So the thing with this is that primarily the 2 annotations which, if you're writing libraries, you're going to want to think about are no target annotation, which is an annotation which is not attached to anything in the circuit, doesn't refer to anything. If you want to think about this, it's like saying there's a build directory annotation. Technically, it's called a target directory annotation, but it's something which is just saying I want to control where my files are going to be output. All right. Alternatively, you have a single target annotation, which is a target which is an annotation that is targeting one specific thing. And that thing, in the current sense, extends names, but really what that is that's a target. Okay. Eventually, there will be a multi-target annotation, which is something which is able to be attached to a sequence of things, or a sequence of targets in your circuit. Okay. So building out all of that, right? Given the fact that you have these no target annotations, you can then develop a concept of what we've been calling a stage. So the hardware compiler framework is consisting of some number of stages that you're running. It's not necessarily a front end, a mid end, a back end. There may be 20 stages going through this. So if any of you attended the rocket ship tutorial where they went into some of the details of diplomacy, diplomacy is kind of like a pre-chisel stage. It's not necessarily implemented as such, but I'll get into some of the details how you think about that. Okay. Now, alternatively, if you think about this target directory annotation, so this is something which is controlling where my files are going to be output by the FIRRTL compiler or the Verilog emitter. Okay. There's a fungibility, a direct fungibility of that with command line options. So we've been doing a lot of work under this a specific RFC 764 on FIRRTL, which is trying to then unify all of the annotations such that all command line options that you may pass to any stage in the hardware compiler framework actually are mapped to annotations. Once you have those annotations, you can just read them in whatever stage you have, and then that's controlling what happens in your circuit. So in this sense, it's just trying to unify on what it means to be something which you as a developer want to then go and include in the Chisel3 Hardware Compiler Framework. Okay, it's a little bit of a subtle concept. I'm happy to talk more about it offline. But alternatively, you may be able to then get pretty far just by looking at the original RFC for this, or by going through some of the patches which have then actually then introduced this at the FIRRTL level. Eventually, this will then go and percolate through all of the stuff in the big 6 repositories, which is Chisel, FIRRTL, Chisel testers, FIRRTL, pretty much everything in this ecosystem. And then there'll then be some effort on trying to include this for other things which are kind of like stages. Okay. So with all of that in mind of what this hardware compiler framework is, there's now sort of the necessity to then build and think about what is sort of an ontology for libraries within the hardware compiler framework. Okay. So the first thing is it may actually be best to first kind of just touch on what level 2 is, or enumerated or bullet 2 here is. So when most people think of libraries in the Chisel, within the Chisel ecosystem, what they're thinking about is something like a new queue or an arbiter or something that could eventually be merged with a standard library, right? It's something that subclasses Chisel types, okay? And that's, for the majority of users, that's what you're going to then be dealing with, okay? You go and you build a new machine learning accelerator that extends module. You can then go and then you publish that on Maven, and then somebody else can go and import it and use it. However, there's a lot of other ways that you can interact with this ecosystem, and that's kind of why it gets a little difficult to then think about what a library is. And I kind of go through these all in detail, and give a lot of examples of what each one is, just to kind of get you familiar with all that. All right, so taking a step back from bullet 2, if you go back to bullet 1, so then you have things which are front-end like, okay? So these are a stage that runs before FIRRTL. I'm not specifying how soon it runs or if it runs right before FIRRTL, but it may run, many stages before FIRRTL. So an example of this would be something like something that is front-end like is also something that behaves like Chisel. Okay, it's something which eventually emits FIRRTL, but it may emit something which then will then pass through another stage and eventually emit FIRRTL. On bullet 3, you have things which are mid-end like. Okay, so these are things which behave like the FIRRTL compiler, or there's something which are FIRRTL transforms which the FIRRTL compiler uses. So fundamentally, it's something which manipulates the FIRRTL AST. Then you have things which are back-end like. So this is some stage that runs sometime after the FIRRTL compiler. This may consume FIRRTL IR, or it may consume something that the FIRRTL IR was converted to. So everything in the back end, like, you could also sort of classify as tools, synthesis tools, place and route tools, or some of the work like what Edward Wang was then working on, where then he's then reading in Verilog and then generating tickle scripts, which are then going to run the Cadence and Synopsys tools for actually getting down to GDS. All right, so even with all of these bullets 1 to 4, once you have this concept of annotations, you can then build libraries which cross multiple levels. So the difficulty too is that a library can also be some permutation of the above. So a classic thing which we'll get into is like the notion of boron utils. Boron utils has a Chisel API, but it's backed by a FIRRTL transform. Granted, you can also think about something which has a Chisel API, but is consumed by a Verilog emitter to then change how that behavior is. So you wind up where the libraries are something which are able to sort of cross this hardware compiler framework stack. So I realize this is all kind of amorphous, but there's a fair number of examples getting into this. So what I generally then introduce is the way that the rest of the talk is structured is that you have there's sort of these tables, and they're broken down into what a specific project is, or how I've kind of classified it. In each one of these, all of the names on the left are they're actually linked, so you can go and click them. But the convention here is just the first thing is the GitHub organization or user, and then the next part is the project. So this is like free chips, or this is github.com ucb/chisel2 deprecated. Okay, so first, so the reason why Chisel2 is a pain in the neck is because it is the entire hardware compiler framework. It's like the GCC of hardware compiler frameworks. It defines a new language defines a DSL for talking about hardware things. It's also a front end. It also provides a standard library. It also has transforms, and it also has a back end. So the real thing here, and the real thing which kind of pushed things from Chisel 2 more towards Chisel 3, is for something like the Strober or the Midas project. You have something where you want to go and then add transformations which are going to automatically optimize your circuit so that it'll run better on an FPGA. And if you aren't able to, easily hack on the transforms and hack on the mid-end, this is very difficult. Okay? So this is sort of my view on why you shouldn't use Chisel 2, is mostly because if you want to then go and hack on it, you're not going to be able to. All right? So jumping right in now talking about what are things which are front-end like. Okay? So obviously Chisel 3 is something which is a front end. It defines a new language, and it additionally emits FIRRTL. So it's something which runs before FIRRTL, but it also defines a language for describing circuits. Okay? There's other work done at Stanford on a language called magma. Okay? Magma, which has been, like, even by the authors, has been described as like Chisel in Python. Okay? So the thing is here, this is also describing a new language for talking about hardware with its own DSL, but it's something which can target FIRRTL. It doesn't sort of by default try and do that, but it's something that can target FIRRTL. So this is something where you can think of magma as also a front end for the Chisel-FIRRTL Hardware Compiler Framework, even though it's sort of Chisel-FIRRTL Hardware Compiler Framework less Chisel. Similarly, Halide FIRRTL, a Berkeley project I'm not super familiar with, but something we're able to go from the Halide language and then target FIRRTL directly. Okay, another Berkeley student, I actually think this was the work dealing with some prototyping for the guarded atomic actions. But you could also then just write your own front end, which is then able to go from Python and target FIRRTL directly. Okay. Additionally, now this is where things start to get a little weird, right? So then you think about, so yesterday we had a talk from Stanford about spatial. Okay. So spatial is a language that is able to emit Chisel. So this is something where it kind of starts to blur the line on what you mean is a front end, right? So it would be equivalent to a Python program that emits C that is then consumed by Clang that LLVM optimizes that is targeted for an x86 backend. It's kind of like that. So I'm still calling this a front end, but it's something which is kind of similar to a front end, but a little different. All right. Now, similarly, what gets kind of confusing, so there's an open source synthesis tool developed by Clifford Wolf called Yosis, and Yosis is able to read Verilog and output FIRRTL. So by that definition, it is something which is, it is a front end. However, it also is able to optimize Verilog directly, so it kind of has transforms, but it's viewing Verilog as the IR. And then finally, it's also kind of like a backend because it can also read the Verilog and then try and do synthesis on that. So this whole thing gets like very confusing once your Verilog is on both ends, but it's totally reasonable. So this may seem kind of weird, but something where once you have Yosis as a front end, or Yosis is integrated with this whole system, you can think about things like where you would normally, I think the standard compiler term is like link time optimization. So this is something where, like, if you had a black box, you could then use Yosis to then read in the black box in Verilog, convert it to FIRRTL, and then inline it in your circuit. All right. So there's all sorts of crazy things that you can start doing once, it's not just Chisel, FIRRTL, Verilog, but there's all of these other stages that then you are then able to interoperate with. All right. And then finally, there's a program, or there's a project for converting VHDL to Verilog. And this, if you stacked it on top of Yosis, would then be like a pre-front end on Yosis running into all of this. So I have two examples of what these actually look like. So this was taken, I've not really played with Magma, but this is taken directly from one of the examples that they provide. But basically what it is they're defining a circuit main that has 3 inputs, A, B, and C, 1 output D. And then D is a couple of Boolean operations on A, B, and C. And finally, then they go and compile that, targeting the build directory build/main, and they're trying to output FIRRTL. Okay? So that, you then go and run it, and this is a FIRRTL circuit. Okay? So the one thing here, which, while, I mean, I like Chisel, I like to write in Chisel, but if there are other abstractions which make a lot of sense, I would highly encourage you to not go and write a Verilog compiler. I would encourage you to go and write something which is targeting FIRRTL, because then you're able to leverage all of the hard work that people like Adam and Jack have put in to build all of these optimizations, and you can just use them directly. So it's like if you didn't go and do this, and you say, well, I have the best abstraction, and I want to go and write, a front end for designing hardware in what's the most obscure language I can think of? Well, Apple. So APL, ancient language, kind of came out of IBM, use a lot of symbols for describing things. The first thing that you're going to do is you're going to realize, I'm going to use this language, and then I need to go and write a dead code elimination task. Well, the thing is, FIRRTL already has that. If your job is only to then target FIRRTL, you can then automatically use that. You don't have to worry about having to re-implement all of the algorithms that other people have. So you don't have to do that, but it's something which is just sort of highly encouraged. Right? So Yosis is then able to do a similar kind of thing here, in the sense this is just a simple Verilog module that I'm reading into Yosis, clock AB F. It does some, I think, yeah, this is just a simple multiplier. And if you then go and you run that through Yosis and you say, hey, I want to go and read this in as Verilog and I want to output FIRRTL, you then get your FIRRTL here. Okay? Obviously, this is not going to be terrifically readable. But if this was something where you wanted to then say, this was my multiplier black box, and I wanted to go and inline it inside of my inside of the FIRRTL compiler, you could then go and do this. All right, and just feel free to stop me if there's any questions about any of this stuff. But this is a little bit of a shotgun kind of presentation. It's a little bit it's just because it's a little difficult to kind of sort of lock down what a library is. So I'm kind of trying to whet your appetite on what libraries exist that you may want to use, but then also once you have a hardware compiler framework, what types of things you can build. All right. So bullet 2, these Chisel3 pure libraries. Okay. So these are things which you would think of as either the Chisel3.util, which was already pointed out, is basically the standard library for Chisel. So this is a pure Chisel library. It defines classes, and those classes subclass Chisel types. They are modules. They may extend decoupled I/O, etc. Okay. Chisel Testers 2 is also much closer to a Chisel library. DSP tools, which you've heard some about, this is also a Chisel library, as well as implementations of specific microprocessors, things like RISC-V Mini, Crecilio's Boom, Test Chip IP, which is sort of a collection of things for helping you actually build out build an ASIC. Berkeley's hard implementation of a floating point unit, Sci-Fi blocks, the NVIDIA DLA blocks that Sci-Fi has, which is basically Chisel wrappers around NVIDIA's NVDLA. Some stuff that I did for building a machine learning accelerator during my PhD. perfect-chisel, which is IBM developed Chisel IP that came out of the DARPA Perfect program, and so on and so on, including Martin's Chisel examples, FPGA tidbits, MIPS microprocessor, and an AES implementation in Chisel. Okay, so basically this is for the majority of users. Whatever you write in Chisel is really just a Chisel library. So whenever you see something and you're like, hey, I made a nice implementation of some module, think about then going and trying and upstreaming that with Chisel3 util. Okay? So as one example of that, which sort of concrete example from this IBM perfect-chisel repository is just a linear feedback shift register. Okay, it was we were doing some experiments with fault injection, and we needed some way of having pseudo-random numbers being generated. I guess at the time I didn't realize that Rocket Ship also has a very nice implementation of a pseudo-random number generator. But basically what it is I've written so many linear feedback shift registers going back to my undergrad days, and I always have to look up what are the taps for a maximal period linear feedback shift register. So it was very easy, and this doesn't show all of them, but just to go online, grab a PDF of all of the maximal period taps for a certain type of linear feedback shift register, go and encode that in an object, and then build a generator for an arbitrary width linear feedback shift register. So the key thing is whenever you find yourself, you're building something over and over and over again, go and figure out something that's able to generate all possible things, put it in a library, and then hopefully then upstream it with Chisel3 utils. Okay. This gets kind of complex with a lot of functional programming stuff, but basically this is just applying whatever taps. Let's see, the LFSR taps are looked up here. This shiftreg.zipwithindex.map, this is constructing the shift register, and then some of those connections are being overwritten by looking at what the LFSR taps are and adding XOR gates in there. Okay. This is available online, you can take a look, but once the stuff related to the Chisel3 contributor license agreement is sorted out, this will then get upstream. Okay, now you kind of have the island of misfit toys of Chisel3 libraries. So the thing where this gets kind of confusing, and this is not saying that these are not good libraries, it's just saying that they bend, they're not very clear cut in saying that they're just something which extends some Chisel3 classes. These are things which are providing new abstractions on top of Chisel or are kind of bridging the gap with some backend. So like the existing Chisel testers library, which will eventually be replaced with testers 2, includes a bunch of stuff for emitting sort of Verilog testing associated with it. So it kind of blurs the edge and includes things related to a backend. All right, I don't know if there's a clean way of actually separating that, but it's just the state of the world. All right, now Rocketship, which I'll get into more detail specifically, and I break this up in terms of Rocketship and Rocketship diplomacy. So on the one hand, Rocketship is a front end because it makes calls into methods of the Chisel3 driver, and it also provides a bunch of things which extend Chisel3 classes. Okay. However, diplomacy, on the other hand, is effectively a new language for describing graphs, and it's also something which technically is running before Chisel. So it's one of these pre-Chisel front-end kind of things. But it also provides, subclasses modules in Chisel3 stuff. So I think if you attended Henry's talk earlier today, probably on Rocketship, you probably saw some of this. But this is just sort of the way that I like to explain in the concept of libraries. All right. So diplomacy at the same time is three things. It's a Chisel3 library, it's a language for describing graph, and it's a pre-Chisel front end that added via a singleton above module. All right. So I'll come back to this in a second. What that really means is, so in Chisel, things get a little confusing because there's a class module and there's an object module. You have to wrap module, so you have to use the apply method of module, which is where normally you wrap something. You say module like new foo close parentheses. Okay. So what that's really doing is what Jack kind of got into earlier, is that's interacting with this global mutable state stored in the builder. So in this sense, what it is you have module, this has an apply method, you have to give it something which extends module, class base module in this case, and then that's going to go and actually instantiate that using interactions with the builder. All right. The thing is, I can just replicate this process again, which is effectively what diplomacy allows you to do. So in this sense, you have LazyModule, and LazyModule is a class, and then there's also is abstract in something which extends, technically this extends raw module, but just think of it as extending module. So the thing is, LazyModule and the LazyModule object are analogous to module and the module object and the class module. It's basically just all that's then going on here is that you're saying, I'm going to have my LazyModule object, I'm going to do some stuff in that, and then I'm going to do the instantiation. So the thing is, you can replicate this process indefinitely if you want. You can say, then there's a lazier module, laziest module, whatever. But really what this is doing is it's a way of then providing hooks so that you can do something before you do your elaboration. Sure.
So I'm just trying to understand, is this kind of an attempt to make a pure class?
To make a pure class?
Pure class is like a class that can never be instantiated. You always have to extend it.
No. This is abstract. So that's kind of what I think you're getting at here.
Yes.
But yeah. So I mean, this is abstract, but it's not like a hack to try and make an abstract class. It is abstract, but it's basically just saying that it's abstract, and you have to implement something which is going to instantiate a module, or can be instantiated.
Okay.
So the thing is, you can then replicate this again and say you have something which is abstract in a method which is going to return a lazy module. So you can keep kind of going, stacking this up if you want. Yeah, Henry?
I think the slide is missing there's also an object.
It's missing the object, yeah.
There's an object lazy module which has an apply method.
Right.
Which actually will make your concrete subclass of lazy module.
Correct, yeah. So I was trying to get this done right, or get this added right before it, but yeah, Henry's exactly right. On this slide, just like on the previous slide, there should be an object module, but object lazy module. But basically just trying to get this idea of you have something which is intending to run before you're doing your normal elaboration. Okay, so the thing is, I think it would be relatively difficult to try and add your own thing inside of diplomacy, but this is a pattern that you could use if you wanted to, right? So just to clarify, this is sort of this, I don't know what to call it, so I've been calling it just a singleton pattern. You introduce a singleton to track something you care about. In this case, you have object lazy module. You force users to wrap calls to an apply method of this singleton. And then you require that users implement an abstract method that can be used to construct a chisel type, in this case class lazy module, and you use the information the singleton provides when pre-elaborating your chisel. So it's all a little complicated, but really all that's saying is you're trying to do stuff before chisel runs.
Is there a plan to add like a pre-elaboration hook into the chisel compiler itself?
Yeah, just the question was then, is there a good way to add pre-elaboration hooks into Chisel? That would probably be a really good request for comments, because that's something which would not be easy to do now as far as I'm aware. So related to that, so the whole notion of when Adam and Jack were talking about these chisel annotations, so chisel annotations are something which is effectively happening after the elaboration. So it's kind of like the chisel annotation is kind of a hook for emitting annotations after you've elaborated your circuit. But there probably does need to be more ability for you to add things that happen before or after the specific elaboration, then allow it, but I'm not aware of anything that specifically come up with that except for diplomacy.
Yeah, so why do you ask? Do you have like a specific use case?
Just for like, say, doing something like what diplomacy is doing, but as part of like not really making it the oddball of front-end library, more like a back-end.
Yeah, Henry.
Yeah, I don't want to muddy the waters further, but I think actually two things. One is I think part of the challenge to adding pre-elaboration hooks is the fact that the way Chisel works is these modules are elaborating hardware inside the Scala class constructor, right? So as you're creating a module hierarchy, you have these constructors calling constructors, right? And so I think that was a very early design decision that has been kept and does sort of make it more Verilog-like, but it has the side effect of you can't create the class, manipulate it, and then call like .elaborate on it to find
Right.
everything. So that's what leads you down this road of using this singleton pattern to try to get out in front of it. I think another related point is also that you can sort of embed calls to lazy module and calls to module within each other. So you could have a top level non-lazy module can also, even with just these two existing steps, you can kind of toggle back and forth between the modes in a kind of nested. I don't know what point I'm making, I just find that interesting.
Yeah, no, but the thing is, like, once you start thinking about all of the possible things that you can do, it's a good thing that people are aware that, you know, you can use that pattern for doing complicated things which may come up. The thing is, there hasn't been, with the exception of the parameter negotiation stuff in diplomacy, of something that I'm aware of where you really need these pre-elaboration hooks. But if that's something which is what we wind up needing, then it can definitely be added. Was there a question in the back? Okay. So, all right. So now, then getting into what are things which are kind of mid-in-like and/or FIRRTL transforms. Okay. So obviously, FIRRTL is a mid-in. It includes transforms, but it also kind of bends it because it provides a backend, right? Okay. With that, then you have things which are sort of classified in the upper middle here, which are just things which are pure transforms or pure mid-ins. Okay. So like Chick's visualizer, which I'll show on the next slide, is basically a way of walking the AST to emit a GraphViz visualization of what that circuit is. Barstool's things that Berkeley has used for helping them tape out chips. There is actually a re-implementation of parts of the FIRRTL compiler using Haskell, I believe. So something which is kind of like a transform, kind of like whatever it is. I mean, potentially something that may be very useful for, or even as an exercise, if you wanted to go and write that, for actually really understanding how FIRRTL works without having to actually, well, I don't know. That's it's kind of the point of if you wanted to write something which is able to then operate on LLVM IR, it's probably easier to just write a transform that you implement integrate with LLVM. But it's just these are other things that exist. There were a number of talks about some of the Intel passes that they're able to use for doing power and area timing and area estimation, which in those in this sense are pure transforms. And then there's another similar project or another similar repository similar to Chick's visualizer, which is able to take a FIRRTL circuit and convert it to GraphViz. Okay. Now then, related to that, then there is also, I believe, a C++ FIRRTL compiler called FIRRTLator.
I think it's a FIRRTL front-end for Verilog.
It's a FIRRTL front-end for Verilog?
Yeah.
Okay. So I guess I have that wrong here. And then inside of, so those are all things which are clearly transforms or mid-in-like. So then the thing is, then you start having APIs which are bridging the gap between Chisel and FIRRTL. So some of these things are in the Chisel3 utils standard library, things like what you've seen, boring utils, inline and flatten instances, as well as the load memory transform. So inline and flatten instances, these are things which allow you to collapse some of the hierarchy, to collapse one level of hierarchy or to collapse the complete hierarchy from a specific instance on down. And load memory transform is something which allows you to say, I have a memory and I would like to be able to then load it. Once it's in Verilog, I would then like to be able to bind that to some actual initialization. Related, Midas, in a different sense, is something which defines Chisel library, which defines new Chisel types, but is also a set of transforms. And those transforms may use inline compilation to call into and build new constructs from the Chisel library. Kind of complex. Another project that came out of IBM doing sort of similar kind of things, but not quite as robust, but for doing runtime fault injection. So digging into this, there's one example from the straight transforms and one example from, or I guess two examples from these things which bridge the gap. So this is just an example. I think this was actually shown, or a version of this was shown before, but this is showing the output of Chick Markley's Chisel visualizer. And really what this is something which is able to then, you just walk the FIRRTL AST. Whenever you hit a node, you emit some, I guess this is using SVG, so you emit some SVG. And then when you're done, you have an interactive graph or an interactive plot that you can then go and click on. Okay? So these types of things, like if you're trying to say like, oh, I don't know what I should do. I would like to write a FIRRTL transform, but I don't know what I should do, and I want something to play with. Writing things like this is very, very good for getting acquainted with it, because it's also something where you're not modifying anything, you're just looking at it and analyzing it, and then emitting something coming out. So again, pure transform. Just read in the IR, emit something on the side, and then dump out the IR without modifying. All right, now I dive a little bit more in on boring utils. And boring utils, just to be clear, boring utils is a Chisel API for talking with the FIRRTL wiring transform. And what this implements is the ability to do soft connections. So basically connections which do not exist at the Chisel level, but FIRRTL is going to resolve sometime later. Just slower on the example that I showed yesterday. In this case, you have top. Top instantiates foo and bar. These don't really have anything else inside of them. They extend raw module just because I didn't want it. I don't care if they have clocks, and I don't care if they have, and they're not intended to have any I/O. But I have this boring utils object with this boring utils method, which is basically saying, hey, I want to go and take foo.x. So this is inside of foo. So this is this wire inside of foo, and I want to connect it to a wire inside of bar. All right. This is a connection which then, if I then go and then I elaborate this circuit and emit chirtle, I get a circuit which doesn't have any of this stuff connected. So like if you just look at the bottom of this, you see top, it instantiates foo and it instantiates bar. Okay, if I didn't have this boring utils board directive, you know, the circuit would look exactly the same. Okay, the thing where things change is that the annotations that are coming out of this are different. So if I was just to elaborate this circuit without doing any of the boring utils stuff, there wouldn't be any annotations associated with this circuit. However, I did run bor and say I want to connect top.foo.x to top.bar.y. And for that reason, then you get the source annotation at the top and the sync annotation down at the bottom. And note that both of these are keyed by a pin. So basically what this is saying is all of the source annotations I'm going to connect source annotations keyed by X to sync annotations keyed by X. So the thing is here, then you can obviously then, when you're doing this, so this boringutils.bor method, that actually goes and that figures out what the key is supposed to be, or what the pin is supposed to be, and it does that in a safe way using keeping track of any other times that you may have tried to bore through the circuit. So you can safely use this. If you go and you're emitting source and sync annotations manually, you may have conflicts, you may have to be careful about how you do that. But the fundamental thing is then once the FIRRTL compiler then goes and runs, you then wind up with something where, as opposed to before, we had just at the bottom here, inst foo, inst bar. Now you have inst foo, inst bar, you have a node X, and that's then bridging the gap between a new input or a new output in foo to a new input in bar. Okay? So you can use so the thing is with this, you can use boring utils as just a Chisel API, or you can use the wiring transform directly. So the next thing, and part of the reason why I went through a large refactor of how the wiring transform works, is to enable all of this fault injection library. So building on top of that, what this basically came down, how this whole project started was that it was some idea of trying to say, for a circuit, I would like to approximate low voltage operation by injecting some faults. All right. So what that basically boiled down to is that there is a sheaf, or it's a project called Chiffre. There's a Chisel library, which is something for allowing me to annotate things, as well as define fault injectors. Then there's a set of FIRRTL transforms, which are going to go and stick my fault injectors in my circuit and wire them up with a scan chain. And then finally, there's something which I won't get into, but basically just a Scala utility for configuring the scan chain. So what that actually looks like, in the sense here, I have a fault controller, so something which I would like to then be able to use to move data through the scan chain. And then I have my module here at the bottom, and what I'm trying to do is I would like to be able to make registers X, Y, and Z runtime fault injectable. So what that is there's this, I import the sheaf library, I say that my controller is a sheaf controller, and I say that it has some identifier. In this case, it's going to be connected and controlling the main scan chain. I declare that my module is a sheaf injectee, and I'm effectively calling into methods defined in the sheaf injectee trait, which are going to emit annotations. Okay, and I'll show what those annotations are in 2 slides. But basically, what this is saying is that X is going to be attached to the main scan chain, and I want to use a linear feedback shift register injector on that. I want to then be able to do stuck-at faults on register Y, and I want to do like a cycle-based injector. Like I want something to fire on cycle 1024 for register Z. Okay. So the thing with this is when I go and I start with this circuit, none of this stuff. The injectors don't exist, and the circuit is left unmodified. So in the sense, it's similar to like this notion of soft connections. These are, I want to queue up modifications that I want to make to the circuit at a later time. However, this then goes and then emits a bunch of annotations here, which are then saying that I have at the top, this is then showing that I have my controller, and then the bottom 2 are then talking about specific injectors that I want to add. Okay, so this is truncated just because this is a big example. So unfortunately, the output FIRRTL is too complicated, is too long to actually fit on this slide. But there are test cases that you can then go and then actually just get from this repository, go and run them, and you can see this kind of thing. But it's a lot easier to just kind of show what's going on here graphically and just kind of just trust me that all this is happening behind the scenes. And I show the modified Verilog here at the bottom, right? So initially, in this case, what I'm trying to do is I want to make X runtime fault injectable. So I have a fault controller here on the left, which has some scan chain that I want to be able to hook up to my fault injector. What I'm doing is then I go and I add a bunch of I/O to my specific module to then add that. I stick the fault injector in the circuit, and then any old references to register X I replace with a connection to the output of my fault injector. Okay, so the fundamental thing here is that, and I originally tried to write this using a Perl library called Verilog Perl, and that kind of worked, but I had to fall back to like some regular expression and some kind of like macro replacement kind of stuff. The key thing with this is that this type of operation is, I guarantee you, going to be impossible for Verilog or VHDL, for some Verilog or VHDL that some engineer writes. Okay, because basically the complexity boils down to parsing the Verilog or the VHDL into some representation that you can manipulate. Okay, if you think you can do this with regular expressions, you can't. It's going to break down eventually. So the fundamental thing here that something like FIRRTL provides is it provides a circuit IR that you can manipulate, and it's relatively contained. You know, it's not a really, Adam was able to go over it, you know, in 10 minutes or so. There's not a huge amount of complexity to understand, and transforms are not super difficult to write. However, doing this with Verilog is completely intractable, except for certain sort of cases of very well-structured Verilog. All right. So just to give you some ideas of this kind of stuff that you can do, and so the Midas and Strober projects, which are then enabling FireSim, are doing very similar kind of things. It's just I happen to have slides for this. And that's basically what you're saying is, like, if I want to do state snapshotting on register X, it's a very similar kind of thing. I want to go and stick something in the circuit, which I can then use to read state out of that, and then I want to have some other path that I'm able to then pull that data out of the circuit. All right. All right, and then finally here, then we come to things which are true backends, so things which are only going to run after FIRRTL. Okay, so currently FIRRTL includes a couple of different emitters, so things which are kind of backends. But it may make sense to have some discussion on just kind of making those more clear that they're not in FIRRTL proper, but they're emitters associated with this framework. So currently you have like the Verilog emitter and the FIRRTL emitter, which are the only two emitters which currently exist. But once you have low FIRRTL, it's basically like just textual replacement to get to, or once you've done some optimization in the low FIRRTL, it's kind of like textual replacement to get to Verilog or whatever other language you have. And I'll show a little bit of that on the next slide. You then have the FIRRTL interpreter and TREDL. These are both ways of actually running and executing FIRRTL. Use FIRRTL. The FIRRTL interpreter is being deprecated eventually in favor of FIRRTL. And then finally, you have something like Edward Wang's hammer, which is a backend in the sense that it's consuming FIRRTL and then running synthesis tools, synthesis and place and route tools. Alternatively, if you wanted to, sort of lump in the set of all possible synthesis, any possible tool which reads in Verilog, it would also be reasonable to call that a backend. Granted, for any of these synthesis tools, part of the reason why you need the Verilog emitter is because that's something they all understand, but you could really then say that you had a synthesis tool which was able to directly operate on FIRRTL, and then that's sort of a cleaner backend and like this three-stage compiler kind of idea. All right, so these aren't terrifically complex, but like in the case of the Verilog emitter, this is just showing a snippet of code from the Verilog emitter. This is looping over FIRRTL primitives in your AST, and then in this case of like add, you convert that to a plus. Okay. In the case of as uint, you add a Verilog $unsigned. As sint, you add a $sign. Once you're at this optimized low FIRRTL level, it's sort of this notion of just a nice, easy replacement on most of these signals. If you wanted to go to some more complicated backend, you may have to do some more complicated optimizations, but for the most part, once you're at low FIRRTL, it's pretty easy. All right, so that kind of is the whole view of what are examples of possible libraries in the FIRRTL Hardware Compiler Framework, which may either give you some ideas of what you can directly use or some ideas of what is possible for you to build. And I think I just have like a couple more slides on some future directions on where things I think are going to be going within this space. So the first thing is this notion of the deployment and the rollout of this stage concept. So stage, again, is this abstraction of anything in the FIRRTL Hardware Compiler Framework is something which is able to consume annotations and emit annotations. So this comes down to then, this is actually currently upstreamed in FIRRTL. There's a package FIRRTL.stage.FIRRTLstage, and you can use that in place of the FIRRTL driver if you want. There's a pending pull request which converts the old FIRRTL driver to then call the FIRRTL stage on the backend. Or not to call it on the backend, but it converts it to a shell that's then calling the FIRRTL stage. Eventually then that'll get propagated over into Chisel and then into all of the other repositories that exist within this ecosystem. And then assumedly then that will then make it easier for other people to then interoperate with this. Because then it's sort of like if you want to integrate with this ecosystem, then all you have to do is emit annotations, and then the annotations are picked up by something else in the hardware compiler framework, and then they execute. Now, obviously, it's beneficial if the owners of these specific projects are then able to write wrappers for this or able to implement it within the stage concept. So this is like if you have your, if you're the author of like MyHDL or something like that, and then you want to then be able to target FIRRTL and operate with this ecosystem, it's really nice if you provide like a small scale-up program which is then implements the stage and calls out to your stuff, and then we can then kind of nicely integrate it with this. If you have more questions about FIRRTL stages, I'm happy to talk about that, but there's also a pending pull request related to this. And also this is issue 764. All right. So finally, so one of the things which came up is like Chisel3.util. I mean, this is fundamentally a standard library. There's a pending pull request here, or not, there's a pending request for comments here, which is talking about what things people want to see in the Chisel standard library. Okay? So chances are there's a lot of things that people have already written, which are probably nice candidates for upstreaming. So that's something which, if you have stuff, either comment on this RFC or file pull request on Chisel3util directly. And honestly, I don't really know what the boundary is between what's like useful for just you and what's useful for other people. But part of it is just trying to make things easier so that people aren't having to continually re-implement stuff. It's just it's just genericizing like the example that I gave of like writing a linear feedback shift register. Fundamentally, you shouldn't have to write that. So if you have stuff related to that, or if there's stuff that you would like to see, make sure to comment on this so that we can then get, if people have time, work on implementing this so that everybody can use it. And then finally, there's new front ends, new back ends. So one of the things here is that like Chisel is a fantastic language for then talking about describing arbitrary hardware. But sometimes you want other abstractions. So it's like the talk earlier about tensile. If you're saying if there's something nice where like TensorFlow is a very nice language for describing graphs and for describing machine learning computation. It works very well. And the thing is, there is potentially some way of then either treating that as a true front end, which is either targeting Chisel, or as a front end which is targeting FIRRTL. And what that really comes down to is if there is some domain-specific language which works better for a specific domain, then that's potentially a candidate for something which is included in the FIRRTL Hardware Compiler Framework as a new front end. In the sense of a front end is something that runs before Chisel. Okay? People have asked for this intermittently, but the VHDL backend, part of the reason why nobody's really pushed on this too hard is because pretty much every synthesis tool supports a mixed environment. So even if you write stuff in VHDL, you can usually then do imports from Verilog.
You cannot use the free model sim version in mixed language.
Okay, so
that's a problem. Okay.
So no, I mean all this is about reducing friction. So Martin was saying that you can't use the free version of model sim with mixed mode Verilog and VHDL. So in that sense,
restriction now.
So if we had a VHDL backend, that would potentially be nice. Granted, one of the problems here and the other concern about this is that, like the Verilog backend, we know it works. Sci5 has used this to tape out many, many chips that also work. Once you have different backends, then there's some concern about, are they doing the same thing? Are they equivalent? It's an open problem, and that's also part of the relation related to a new C++ backend. So the question came up, so Chisel2 used to emit a C++, a bunch of C++, and also Verilog, and the intent was you compile the C++, but that is equivalent to the Verilog, so you just do your simulation of the C++, and it's nice and fast. Verilator got a lot better, and then Verilator, it makes sense to just compile the Verilog directly, and then you remove this problem of making sure the C++ and the Verilog match. But there may be some effort in the future going forward, or if one of you want to drive that, of then saying, well, maybe it makes sense to revisit this, because potentially at the FIRRTL level, you're talking about a nice circuit graph, and you may be able to make some optimizations on that, which can then be used to build, say, a nicely parallel C++ emulator that is going to beat Verilator as long as you have, nicely partitionable things. So it's just something to think about and something to potentially look at. But that's basically the end of this. I can try and take any questions, or I will take any questions. So just let me know. Otherwise, we can adjourn and for a little bit and then move on to the birds of a feather.
Yeah,
Sure.
So let's say you have a library that's just like Chisel code, like what would you find like I don't know, I know what your method, like what your classification was, but like so like just like a regular Chisel library. And then at some point you're like, oh, there's something I would like to do with an annotation and a custom pass. How do you package that so that someone can like just like include the native package and automatically have it like work? Because like some people call Chisel a different way.
Yeah.
Tests and in like when you want to generate Verilog, what's like the most user-friendly way to package it so that they can just like include the library and then also have the password at the right stage?
So the most useful way to do that is to publish to Maven. So really what that means is that you're taking your project, you're packing up all of the jars, and then you're then going and sticking that somewhere where people can then download those jars. So for the case of like Chiffre, so alternatively what you can do is once you go and so like the FIRRTL compiler needs to find transforms which you may have defined in some jar. So the thing is, you can just provide the class path when you like call SBT using Java, give it a class path, and tell it to also go and look in your additional directory, and then all of those transforms will be available to you.
Okay, but that doesn't really work. So like, I don't want to like tell the user how to call this BT, right? Because like they might be just like using like IntelliJ object or something.
Yeah. So in that sense, then like get your project so that it's on Maven, and then they can just handle it from SBT of then pulling that in, and then it'll just work.
So where would I put my, so I have my transform, and I have that maybe like in my code, in my project, right?
Yep.
So then how do I get that injected into FIRRTL? Like if they like link to FIRRTL, like the Maven package.
Yeah. Okay. So in that sense, yeah, I'd actually have to think about that. So I mean, the way that I've done it in the past was, it was only because with Rocketship and doing fault injection into Rocketship, because Rocketship calls the FIRRTL jar directly, I just added to the class path, and that kind of made it work.
Right. I just feel like for like small projects, it's easier if people can just make one like Scala project in their IDE and just have it like all like work. Like just do like a little app that just like generates the code versus like building your own like file-based system.
Yeah. So I think you can probably just handle it with imports. So I mean, if you
Or you can also take this offline.
no, it's fine. So the thing is, like, if you do a normal like chisel top like project, you call the Chisel3 driver directly. You've imported from your custom FIRRTL transforms into that. When you then call Chisel3, that is then calling that will then run FIRRTL, but you're giving it options, which you're saying go and look for this specific transform. So you give it like a custom transform option, and if you do it with a string, then that's going to go and try and find that in your class path. And if you're doing that with a project that is already importing that, it'll just be available. It's more of an issue of if you have like a separate FIRRTL jar, and then how you're then trying to then compose all of that. But if it's just like a normal standard chisel project, you call the Chisel3 driver, or eventually the Chisel3 stage, then it will quote unquote just work, which I realize are famous last words, but.
Is there like an index of good chisel packages out there? I mean, slides I guess count as one, but is there a kind of canonical list of like these are the packages that people have published for chisel?
Yeah, so that's actually something that we've been intending to like get on the website, and I think because I mean this was literally just me like searching through GitHub and trying to find like what different projects exist. So yeah, that would, I mean, one thing which would probably be good, I think it would probably be reasonable if people emailed Jim, and or I mean really just email anybody and we'll get the information where it needs to go. So if you do have a nice chisel project, like tell us about it so that we can put it on the website.
You can tweet about it.
And yes, so we can tweet about it. Yeah, no, like dead serious. Just send us your stuff and we'll tweet about it, and then other people will tweet about it, and yeah. So yeah, because I mean one of the things which was kind of an issue with a lot of the outreach stuff is there's a lot of users out there. We don't know what cool stuff you guys are building unless you tell us about it, or unless we go hunting online for it. But if you just want to use Chisel and don't tell anybody, that's great. Use Chisel. If you want to tell people about it, that's great. And if you build something that's like super useful, like hypothetically like DSP tools, it started out as something which is totally sort of independent, but there's portions that make sense to upstream, like intervals. Then please, feel free to get your code so that other people can use it and be more effective.
Yeah, I feel like a page on the website that just highlights libraries and like a quick one sentence about what they do would be good.
Yeah.
I saw 2 libraries on your slide that I was like, I wish I had used those. Like, I'm now going to go look them up, but yeah. Yeah. Okay. So I think if that's it, then we're slightly over time, so then we can adjourn and then resume for Birds of a Feather later.